Recording now. All right. Okay, so here we go. Developed the branch of mathematics that studies relationships between side lengths and angles of triangles. So it's but more. Okay. Also, I'll show you pictures like this. As you find an angle, actually what we call the first quadrant, it really just repeats itself over and over again. If you think of this like season 1, 2, 3, 4, okay? There's so many things in our life that we go up, down, sometimes low, and back up again, and then starts all over, okay? It's kind of like if I show you a heartbeat, it would be cyclical. Your biorhythm, there's many of those that are cyclical. Tons of things, like I said, in life are cyclical, you know, your grades or whatever. But I'll show you this in real time. But do y'all see that really that angle is just going to repeat itself over and over again? And what we're going to do is we're going to use that to our advantage. Because once you learn what all happens in the first quadrant, it just repeats itself with different signs, like positive and negative. Unfortunately, in the English language, we have the word sign, S-I-G-N, and sign, S-I-N-E. Really funny, quick story. Somebody sent me an article one time about, does anybody watch football besides myself? Yeah. Okay. So anyway, it was about a kicker at a university, a place kicker that was kicking goals and extra points, and he had absolutely horrible year. Like, I don't even know why they kept him as a kicker for the next year, didn't replace him, just like a new recruit, but beside that point, hope he's not listening to my video. He was an engineer, though, the media found out. So they went and interviewed him. If I find, I've got it in my filing cabinet somewhere because I keep like real life things for y'all to see. But the person that went and interviewed him, he said, I'm going to be a whole lot better next year because I know trigonometry. And so I'm going to have to get out on the field, and if I can get something that's over here, I'm going to figure out the angle, which somebody has to do if they're actually launching a satellite. They better know how far it is, the angle to launch at. I mean, horrible things like like missiles. You don't just land in the wrong place. You've got to be extremely precise with trigonometry. But your GPS, you don't want to end up 5 miles away from where you want it to be. You've got to be very precise in trigonometry to allow for that. Anyway, he's like, I'm going to go out on the field and sort of think about how far and what angle I need to kick it, because there's different angles depending on where he was standing. And so the guy interviewing him, interviewing him for the sports page, was writing the article, and they said he was going to use sine and cosine to help become a better kicker the next year. I think it was better, but you could hardly be worse, so I don't know if it's a good measurement. But anyway, you know, it's like if you do so bad, any improvement is good. The author of the article in the sports, in the state newspaper that I was in, he wrote sine, S-I-G-N, and cosine, C-O-S-I-G-N. Didn't even have on their radar that there could be something else. So anyway, sine and cosine, their signs, their positive and negative signs will also change, okay? Which right now seems kind of weird because so what you've looked at so far is a stationary triangle. Like there weren't any positives and negatives. It was just like a triangle, and you had sides, okay? So it's really cool to see how it blends together with the math that you already know. So let me look at my list and stay on track here. So I wanted you to walk in here today really familiar with all of your trig ratios. And I hope I almost made it drudgery to where you're like, yeah, I did it. Okay, but you had some kind of application problems to look at you probably didn't want to do and stuff like that. Hopefully you're really familiar with what happens with 30, 60, 90, and 45, 45 triangles, a reminder of your geometry, because we're going to need that for what we're doing. All right, so I just love that picture so much. So it's a really big one, but it would be confusing to write on, so I have these. I wanted to talk first about the bonus from the test. And everybody, and I've seen people that got the bonuses right. I haven't really looked at many of them, though. I wanted to talk about the bonus real quickly, and I think everybody has had the test, right? Nobody missed it? Okay. If you get out your calculators, This is something that, the reason it was a bonus, it was because I hadn't really shown you how to do this. Let me get out my calculator. All right, here's our equation. Okay. You should be suspect of some of the things that we teach you. And if you're not, that's, you're great, you just trust us. But, you become questioning, probably like, when are we ever going to use this? Which is really, to me, ironic that you would ask that in the math class of all places. But anyway, moving forward. I mean, you use it all the time everywhere. They get in a taxi, you talk on your cell phone, you get on the subway, I don't know what you're doing if you're not using applied math out there. I guess you'd just be walking everywhere without a phone. Anyway, you should be a little suspect. Why we factor, when you've got to think, okay, if and when people are using polynomials in the real world, which they are, by the way, what are the chances they're going to factor? It does happen, okay? But many times they're not going to care if the answers are 1.794 and 3.846. Don't you think that would probably be more likely? Okay? Like even in building something, a speaker came to my class one time who was in charge of a big development, and he went by one of the houses that they were building, and he had one of his best carpenters building something that, but the carpenter was a bit confused. He was building, some of you may have these, a wine rack in the bar of this house that was being built for a customer. If y'all have seen those, at least in restaurants, if you don't have them in your house, where the bottle of wine just sits right here, and it just slides right in, and they just go like this, and it's, everybody know what I'm talking about? Now you'll see them everywhere. If you don't know what I'm talking about, just look around a restaurant, and they'll be up against the wall with wine bottles in them, okay? But he was building it out of wood, and so he had the dimensions of a regular wine bottle, which I guess I should look up. I don't know what it is, but say it's 8 inches in diameter. That seems really big. That's a big bottle of wine. I don't know what it is. Let's say 4. Or let's just say the argument that I want to put something in here that's got to fit 4 inches across. That does not help you put the pieces of wood on it. Do y'all see what I mean? Like, just because I know I want the opening to be 4, I'm not building the opening. I want to build the thing around the opening. And also this goes into something sort of like asymptotes, or sort of like very much like a word you'll learn later in the year called limits. Not only do I don't want it to be a little bit more than 4 so that I can actually slide the bottle in, but not much more than 4 because I don't want to waste space and I want it to be snug. Does that all make sense? Okay, that's just another topic for another day. So the carpenter was like, great, like I can just keep, he knew he shouldn't be doing trial and error to like put the pieces of wood different lengths and keep measuring to see if he had the right opening. So this guy's name was Freddie somebody, I forgot his last name, the man that was speaking to us, and he's like, well, I was really good at math when I was in high school, and so I remembered what to do. So I sat down with the carpenter on a sheet of paper, or they drew on a board, or whatever they had to write on at the time. And he showed him this. This is 4. And this, it was going to be a square turned sideways to make a diamond. And so these are 2. And these are 45-45 ratios. And so they could find the length of this board, which would be 2 root 2. Can you see what I mean? But telling somebody to build something 2 root 2, what in the world are they going to do with that? Mm-hmm. Do you see they are going to have to change that to a decimal and then go and do the best they can on a yardstick and cut it? And then it's going to be fine, isn't it? All of that's a great topic for limits, by the way. 2 root 2 is 2.828. What is it? 2.28. Okay, it's carpenter builds it as close as they can to 2 and 2. You see what I mean? So you measure it, then you cut it, and then you build it, and then it works. Okay? So they need a geometry for that, or trigonometry also. The reason I wanted to say that is that's not helpful to somebody who's really trying to do something. I need the decimal. So what I would say is I use technology a lot because you're not going to be able to use it. I think you already know from this class, your technology is not going to be really helpful to you unless you really know what you're doing. So let's go up to this one. Oh, I'm sorry, I didn't really finish like the whole thing I was saying. I'm kind of all over the board right now. So why do we spend so much time factoring if something like that thing on the bottom won't factor, but yet I still expect you to find the vertical asymptotes and stuff like that, okay? It'd be like if you went, well, I'm going to have a calculator, so I'm not going to learn to add. It'd be just like that. And you're sitting somewhere one day on a job, and you have, 3 customers coming in the morning and 2 customers coming in the afternoon, and somebody asks you how many customers you have coming in today. They go, hang on, let me get my calculator. Because you just never bothered to add. That's silly, isn't it? I mean, people give that argument. Right? The kids are going to have calculators. Why do they need to learn to multiply? Because you'll be uneducated, and also you'll be slower. You are going to need a calculator to add certain dollar amounts together. $1,482.13, and then more money like that comes in during the day. I could add that and carry and everything, but I'm going to grab a calculator to do that. Do you see the difference? Yeah. So factoring, I factor all the time in calculus when it's easy. If it's not easy to factor, I grab some technology and I figure out my zeros. I'm not really silly if I don't know the top of that's x plus 2, x minus 2, and I'm going to be slower. So factoring, when do you factor as an elite math student, is when it's easy for you to factor. You could have done it faster, then you type it in your calculator and do what I'm about to teach you today. What I'm going to show you today is slower. That's all we got. It's not all we got. Back in the day before calculators and computers, they would have had to go, one of your worst nightmares that you probably barely remember. You would have had to take the list of possible rational roots. I don't know if some of y'all know this, my students that I taught know this. You could fill in that whole list. Y'all remember that plus or minus 1/3, plus or minus 2/5? There's a big list of factors of the first number over factors of the last number. And you would fill them all in with synthetic division or with your calculator. And some of them would be 0. And then you could go in and factor. That doesn't always happen. You could go through that whole list of possible rational roots, because what's the key word there? There's 2 key words. Possible. These might work. And these are only the list of rationals. They're not considering anything like something real, like 2 squared root of 2. You go through that whole list, and none of them might give you 0. Then what are you going to do? So then they started using Newton's method. Isaac Newton, of course, came up with a way to find zeros. But it's very tedious. It's fascinating. But it's very tedious. In fact, I think our calculators, actually somebody programmed Newton's method into our calculator from what it looks like to me. So thank goodness. Okay? So this thing won't factor. So sorry if you sat around trying to factor it. You can't factor it. I can't factor it, okay? Because it doesn't have, it has irrational roots. And I think you found them, Rebecca. I think. Do you remember? I think it was you that had the decimals. Yeah. Did you graph it? Yes. Just the bottom. Yeah. There you go. Okay. So in our calculators, what I want to do is I want to factor the bottom, okay? I'm already real aware of the only numbers that make the top 0 are 2 and -2. So I'm just going to look at the bottom. So let's get out our calculators. And everybody do this with me. Hopefully you have yours with you. And you'll use this other times during the year too. All right. All right, so let's just put in the denominator, 2x cubed. I'll call it out if you don't know it. 2x to the 3rd minus 8x plus 3. And suppose the top was really ugly also. I could put in the top x squared minus 4. And I'll show you why I'm doing the top right now. I don't really need the numerator right now, though, so I'm going to turn it off. Are y'all okay? Can I move on? You slide over here, and this is like a light switch. Once it's on the little equals, you can turn, I'm sorry, I may be babying you. You can turn that off. And then when you move away from it, can you see that we've turned it off? It will not interfere with what I'm doing right now, okay? But do you see I've separated my numerator and my denominator? In all reality, usually when I do this problem, I'll put the numerator in y1 and the denominator in y2 because it looks better, right? Okay. All right, so now I'm just going to graph it on a standard viewing window. And before you think, well, all that algebra just went out the window, no, it didn't. All that polynomial algebra I use, because what if I don't see the polynomial? There's all sorts of things I can draw in from my algebra teacher. You know, that 2x cubed has 3 zeros. Some of them might be imaginary. There's all sorts of things that you learned about in behavior models and things that you could talk about if you didn't see the zeros. But I see the 3 zeros. Do y'all? All right, now, I don't ever use the trace button, by the way. You're better than that. Don't use trace. So I'm going to go to second, calc, which is right above the trace. Calc, and what do we want to know? 0. Now what you want to do before you do anything, pick a 0 that you want to find and go over to it. I'm not going to go over it today, but there are faster ways to get there that we're not going to do right now. Here's the 0. This does not matter above or below. See the 0, you want to be to the left of it and to the right of it. By the way, if your calculator ever is not saying as nicely as what mine does, and I can update it for you and just get on my computer and give you the latest operating system. Like for instance, when I hit enter right now, do you see how it gives me a bar? And I can see it's on the left. The older calculators don't do that. Now I'm about to try to box it in, so I'm going to move to the right with my arrow key. I'm going to move to the right, just however far. Brianna might move a different amount than Pietra does, okay? As long as she doesn't go over that hump. Once she goes over that hump, it's going to go find another 0, okay? So I'm going to box it in. I'm going to hit enter. I don't ever hit guess. I don't even know why it's there. I never do that. I just hit enter the 3rd time. And so that 0 is negative 2.167. And I haven't created a lot of the bonuses. I just happen to remember. I think it was Rebecca found all 3 of those. So she knew exactly what she could name her vertical asymptotes. X equals negative 2.167. Always give me 3 decimal places. I'm sorry, I'm going to be embarrassing you. And then you could go find this one, and you could go find that one. And you can name your vertical asymptotes, right? Doesn't mean you don't know math. It may mean that you know more math. I feel like to use this in a good way, you've really got to know what you're doing. Okay, now, let me show you this, and I'll go back. Or let me catch you up. What?
How did you do the zeros?
Okay, go second.
Yeah.
Calc.
Yeah.
0. And I'm going to go find another one, okay, Elena? I'm going to move over this hump, and I'm going to stay to the left of that next 0, just somewhere. Okay, so I'm going to hit enter, and then I'm going to move to the right of that 0, enter. And what used to take, we used to have to do a lot of iterations of, not me, but back in the day, a lot of iterations of this by hand.
Oh.
So I always bypass the word guess. And that's another one of my vertical asymptotes.
Wait, how did you guys do that?
Yeah. Pietra?
I'm confused as to how you got it so that it's on y equals 0.
Okay.
When I do it, it doesn't like go directly on 0.
Okay, make sure you're pushing the right keys. Let's go find the 3rd one together. Second, calc 2. You ready? All right, I'm going to move over toward that 3rd one to the right, just somewhere around there. Get with me and hit enter. Now move to the right of it, just a bit. Make sure you're to the right and hit enter. Now it'll say guess. I bypass that and just hit enter.
Got it.
I'm so glad this happened, by the way. Look at this. People will freak out. They go, oh my gosh, I was trying to find the 0. That is negative 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 okay? But you see this is irrational and it's rounded off, so every now and then it is a zero, but you see it's having a hard time calling it flat out zero. I'm glad that happened. If that happens, you've got zero, okay? If you have 0.00075, that's not zero, but you see the difference? All right, now, Pietro, we okay?
Yeah, thank you.
Okay, now, don't you wonder what would you do? I can't call it vertical asymptote if it happens to make the top 0. By the way, you do not have to be good at this yet. This is just intro. I'll just keep showing it to you, okay? I'd love to fill it in there and see if it makes it 0. Wouldn't you? I don't need to because I can factor that one. Do you see the bonus that I actually know algebra by hand also? What if that was something really ugly, like x cubed minus 7x squared? You didn't have any idea. I'm going to go down there and turn it on. To turn it on, you just hit enter. And now I'm going to go to table, second table. And I'm going to hit the letter X. And do you see it filled in the last thing that I just found? Y'all see it? You may not remember the number that I had found, but it makes the bottom 0, but it does not make the top 0. Can y'all see that in table? I think these calculator skills are very, you got to be good at it in AP anyway, so might as well get you sort of ready for it. It makes good sense. It doesn't make life easier. It just makes you able to do more real world problems. Okay. So now, one more thing. Suppose that now I wanted to see it, and I don't want to go through typing all of this in again. Because sometimes in calculus it's going to look really ugly and be really big or something. You just don't want to type it in again. I have a way to put this over that. You might know why I turned those off. I don't want two polynomials going. Is that what you're going to say? I'm sorry, I started with underdeveloped. I don't want two polynomials going on in the middle of what I'm trying to see. So I'm going to turn them off. Okay? Then I'm going to go to vars. Right here under the arrow keys. Vars. See, it lights up in red. All right, now let's see how intuitive this is for you. Look at all those words. Where do you think I'm going to go next? Y vars. Y variables is what that stands for. Y variables. Now guess which one I'm going to pick for now. Later in the year, you'll pick all of those at some point or another. But what are you going to pick right now? Function. And I want to, the way I wrote it today, I want to put Y2 over vars, Y vars, function, Y1. Now I have to retype the whole thing. Okay?
What'd you do when you got the function?
Right. I went down. So I went second. I'm sorry, I didn't. I went to vars, Y vars, function. And then I had mine in Y2 and Y1. So I picked Y2. And now it's already in my Y board. So I wanted to put Y2, then I did divided by and went back and picked up Y1. It's ingenious. It's really, to me, it's so excellent to do this because you've really got to know what you're doing, or this is good. You can be doing this for 45 minutes during a test. But if you become adept at it like you are your cell phone, it's great. Like I can fly through that and turn the graph on, turn it off, do what I want to, find the zeros, plug them in. I can investigate a lot with this, with irrational numbers. Okay? So we'll do that later. That was just on my list of things to do. You are not required to do that anytime soon, and you're not required to do that without a lot more direction. Okay. Now, this is where we're headed. Pretty soon, you're going to be able to answer these questions, like what's the sine of 120 or cosine of 225, the tangent of 300. You're going to be able to answer those rapid fire. Okay, tangent of 300, by the way, is negative square root of 3. All right, you'll be able to answer those really fast, just like if I said 3 times 4 and 5 times 9. Okay, just not yet. You'll get there. But you will need to be able to answer things outside the first quadrant. So let me see how I want to approach this. Let's see. First of all, let's just start with some angle definitions. This is just like boring stuff, but it's got to be established. Okay. We're now going to many times be looking at all 4 quadrants because things spin around, okay? Like for instance, an angle can go over, it can be obtuse, can it? And we really can have angles like that in the real world, so we need to know what in the world to do with them to find all the sizes and angles that we need of the triangle. What we're doing right now is a whole lot more real world than X and Y axis. Most of y'all have seen, I could probably pull it up, like air traffic on like a movie or a TV show, where air traffic controllers are looking at airplanes coming into the airport. Have y'all seen that? Or maybe in like a movie where there's like a war and they're looking at a big graph of like the world, and they've got all these, and it's actually going, you actually see something going blip, 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 blip as it's going around. Does anybody know what I'm talking about?
Yeah.
Okay. So it's going around like this, and it would be like, I think y'all know I'm pretty silly anyway, but, and I don't have room to really demonstrate this right here, but, okay, suppose that I wanted that red eraser, okay? And I go, I'm gonna get that red eraser. That's not how I would do it, is it? If I'm standing here, wouldn't I just turn and go get the red eraser? That's not an X and Y coordinate, that's how I use I'm walking on. So if you're in an airplane and you think, I'm gonna go to Canada, you're gonna be kind of upset at the money you had to pay for the fuel to go straight up and straight over to whatever city that you were going to. Y'all see what I'm doing? What's the airplane gonna do? Turn and go. So it's an angle. You turn 40 degrees and you go however far. Y'all know the airplanes that you're flying in all the time, they get a bearing or a heading. Once they take off, you feel it turn, don't you? And then you go, okay? So all this turn and go, this angle and hypotenuse makes a whole lot more sense. Comment?
Yeah, well, Ms. Markin last year would tell us, like, if you're walking, like, out there, it's like if you cut through the alum parlor or whatever, it's like a lot, it's like the hypotenuse is quicker than.
Yeah, exactly. We got to look at our angles. X and Y coordinates will be the heart of it, but then we will leave them behind eventually after we establish some things. All right, some terminology. This is an angle. An angle has an initial and a terminal side. This is the initial side, and this is the terminal side. At this stage, I don't ask for definitions. Sometimes Mr. Hill's test will have something like, he'll tell them 2 or 3 words, and one of them will be, and some of you have had it before. I just find out a different way to know the definitions, okay? But do y'all see that an angle, I mean, that's pretty intuitive too. There's really no reason to write this down if you understand that picture. Do y'all see it's got to have a beginning and an end, or you don't have an angle. Okay, it has an initial side or a terminal side. Sorry, an initial side and a terminal side. That way we can talk about it. The initial side is usually in what we call standard position, but not always. Standard position is on the positive x-axis. Standard position is on the positive x-axis. And so we usually start like this. Where they're like hands of a clock almost that are laying on top of each other. And then this one starts to open up and create all these different angles. But these are viable angles. We better talk about these. Another thing I haven't mentioned that's really already almost obsolete. The times that you're living in are just going like this. It's really kind of funny that, I don't know what your kids are going to even know that a CD or a DVD, what that even is. I mean, I remember when Mary got me my, when they issued me here's the story. When I left Memphis in November, in the middle of the year, 6 years ago, almost 6 years ago, November 25th, I left Memphis and, I loved my classes, and so we were crying. Some of my kids drove me to the airport. My one-way ticket to New York City are excited for me, but it was also sad. But a couple of the girls had made me a DVD, like a CD of all of our favorite songs, because I also used to play songs instead of and pictures. It was just nuts. But I had my own classroom, so I'll even a little bit more. But anyway, they had made like all these tearjerker songs, like some of them were fun, some of them were sad, anyway. So I couldn't even listen to it for a while. And after I'd been here 2 months in New York, I thought I'm ready to listen to that CD that Catherine and Luke both made for me. And so I got up my computer and I went, I didn't have anything to listen to it on. Like there was no port to put it in. So I go around the city asking for a CD player. People were laughing at me at like Radio Shack. They were like, "Oh, she wants a CD player," and they're like, "We don't have one on 86. You got to go over to 79." And by the time I got there, they'd already gotten a phone call that some ladies wandering the city looking for a CD player. And they're like, "What do you mean, a boom box?" I'm like, "Never mind." I finally got one, but they had to dust it off, and and I put my whole CD in it, and I could listen to music. Okay, but it's funny that that's pretty obsolete already. But to use a DVD or a CD or a Blu-ray, they spin like this, don't they? Mm-hmm. The wheels going down the street, the wheels on the bus are going round and round and round. So they're rotating like per second, hundreds of degrees. Those DVDs, you've probably pulled them out maybe in your lifetime, ejected it, and it's still spinning. Okay? So those things, somebody better understand what happens past 90 degrees because they're going spinning around really fast. Okay? So that's why we've got to go around and around and around. Okay, these sides, though, aren't they captured by the individual radius of the circle, however big it is? Okay, so these are captured, which goes into the first thing that I was talking about. If they're captured, they can only, then they're cyclical.
Wait, I have a question.
Okay?
Is the angle like acute or obtuse if it's like the terminal one is on like the negative y, but like close to the...
I don't really actually use those words acute and obtuse very much. It doesn't come near into play in trig like it does in geometry.
Okay.
And so really, I'm just going to, as long as you have a frame of reference, tell me what quadrant I'm in if I have a 100-degree angle. 1, 2, 3, or 4. Second quadrant. What's a 330-degree angle?
4.
How far away from the axis am I at that point?
3 degrees.
You're already doing trigonometry. Okay? You just found your reference angle. All right? So a reference angle is, were y'all okay with that even if you weren't speaking out loud? 100 degrees is in the second quadrant, 220 degrees is in the third quadrant, 360 degrees is in the fourth quadrant. Okay? So our next word, if it's in standard position, we know we're starting right here. Okay? Now, a reference angle, we're always going to create what you did over and over again for your homework. We're going to create a right triangle until I teach you otherwise. Granted, it won't always be 30, 60, 90. But back to my lecture at the beginning of class, you're going to appear not very well educated if you don't know the sine of 30 degrees is 1/2. I know you don't know that right now possibly, but it's all based on those 30, 60, 90 triangles. Sure, we're going to have angles that are 38 degrees, and I'm going to need my calculator because I don't know the sine of 38 degrees. Okay? But you're going to look kind of silly if you don't know the basics. Do y'all see what I mean? So, and they happen a lot. They're very common angles. Also, today or next class, I'll show you a far better way to measure angles than degrees. So there's the metric system and the English system. Which one's really better? Metric. Which one's really easier once you learn it? Metric. It's not easier to me because I'm not super familiar with it, but it's easier just to move the decimal back and forth. It's a much easier conversion, and we're the only ones that use the English. There's degrees and radians. I don't know really why you haven't been introduced to radians, but it doesn't happen really until right now, but it's kind of a shame because they're better than degrees. I'll teach you that today or next class. Okay, so here's what a reference angle is. So this is our next word. A reference angle is always something that is less than 90 degrees. Okay? A reference angle is less than 90 degrees. The reason for that is, if you look at this yellow, so let's say this is a 30-degree angle. Once I see what happens with 30 as far as the sizes are concerned, doesn't happen over, it's cyclical. Okay, do y'all see what I mean? All right, so why would I try to find these lengths and these lengths and these lengths if it's a 30, 60, 90 triangle just somewhere else? Notice I put it on an axis though, so now we'll have some positives and negatives our way. A reference angle is always how far you are from the closest x-axis. Where most people get confused and give me the wrong reference angle is they're counting up to the y-axis. You could argue the point with me, and sometimes people try, like, well, why does it have to be that way? I think I would go back to why does 2 plus 2 equal 4? Why is the sky blue? I mean, it doesn't have to be that way, but if you do it a different way, you're going to need a different calculator, and you're going to need a different math system than everyone else has. It will probably work, but we're just going to do what they've been doing, okay? Now, so before I do this for you, can you imagine the 4 reference angles that go with this blue one? Don't say anything. And I'm gonna really stretch you here. Let's make it white so you can see it. And by the way, I love trigonometry. It's really fun. Okay, let's say that that is 70 degrees. Does that look sort of 70 degrees just to you? Maybe 65 or 70 degrees? Okay. There's 3 more of those. And why? Well, really, there's an infinite amount, but what happens after the first cycle? It just repeats itself over and over. I can certainly have 300 and 400 and 500 degrees. The CDs rotate at an incredible amount of degrees per second. So anyway, hopefully you're imagining the others. This one here, can anybody tell me how big this one is? It's a stretch, I know. I haven't taught you how to do this. I'm going to teach you how to do it. I just want to see where you are. I'm going to make you think. How big is that angle? This one, as I rotate, by the way, let me show you this. As I rotate from standard position.
Wait, which part?
As I rotate, okay, wait, hang on. Let me be clear. Here I go rotating to certain angles from standard position.
It's the terminal angle of the second.
That's right.
Okay.
All right, here we go. I'm going to do this at first. I think this one's about 40 degrees. I think this one is about 80 degrees or 75. I think this one's 90 degrees. Going like, was that you, Bella, from standard position? This one looks like it's maybe about 100 degrees. What's this one as I continue to, here's my initial angle, my initial side, and do you see how my terminal side keeps changing from the standard position? So what is this one right here? That's a straight angle, 180 degrees. This one, maybe 240. Anybody know what this one straight down here is?
270.
270. And about how big do we think this is? 330, 340? Okay, so that's what I'm asking you, all right? So when we get this next white one over here, I'm guessing from my little bit of instruction so far that y'all are seeing something like this that I'm headed toward, okay? So let's say this one's 70. That's my reference angle. How big is this actual angle, though, over here? 110. What we'll say is its reference angle, though, is actually 70. Do you see that little angle there in the corner? Isn't it the same size as that angle in that corner? So did you just subtract it from 180?
Yeah.
Okay. Now, anybody know what this one is yet? This is 180. How far do I have to go? 250. What did you add? 70. And anybody figure out this one yet? This is 360. 290. Okay, so the way to find your reference angle, in the first quadrant, it'll be self-evident. 70 degrees, 80 degrees, 60 degrees. In the second quadrant, I subtract from 180. In the third quadrant, I add to 180. In the fourth quadrant, I subtract from 360. Hopefully you can tell this about me as a teacher, by the way. There will be a lot to memorize, but as many things you don't have to memorize that you understand will save you lots of time, okay? Some people are probably taking notes, but I don't know that you need to write that down. Does that make sense? If I want to go 70 degrees this way, I'm going to subtract from 180. If I want to go 70 degrees this way, I'm going to add to 180. And how I'm going to find this one? Most of us think in 180s and 360s without me even trying to make it. When I threw this angle up here, most of y'all were saying 330. You were thinking how far you are from this, okay? If I said, you don't have to do it right now, but if I said draw an angle that's 150, I bet all of our brains would think to 180 and not quite get there. We just think that way, don't we? Don't think much about 90 and 270. I'm not counting from there. Okay, I'm counting from, okay, so here we go, and I wear this fluttery dress today, I didn't think about it, but I'm a butterfly, okay? So, a lot of people call it a bow tie, I'll draw it for you in a minute, but it's like a butterfly flapping its wings. Butterfly's not flapping its wings like this, okay? So I'll do this for you, so a lot of it, and you do it for yourself on the test, okay? So, it's a butterfly. Do you see this is the positive x-axis? I'm sorry, this is the closest x-axis. And your reference angles are always got to be this, or we'll start getting different math answers. If you want to say 2 plus 2 is 8, you go for it, okay? But do y'all see this? Obviously, I'm making a big deal about it because I see some people go to the wrong axis sometimes. But do what you naturally do. You naturally think of the x-axis. I'm guessing you don't think of 90 and 270 very much when you're drawing an angle. You think about this, okay? So do you see what I mean by it's a butterfly? Okay. It's originally called a bow tie. Do you see this 1970s big fat bow tie here? Or a skinny 1950s bow tie right here. So what's going to happen is if you want a reference angle and you go around like this, and let's say this was 135 degrees, I'm going to be asking for your reference angle so that I know this triangle right here. So I need this angle, which many times I call theta. So do you see I'll always subtract from 180? I am not looking at 90.
So theta of that is the reference angle?
Yes, it'll be 45 degrees in that scenario. Theta doesn't always mean reference angle though. Theta just means
Just in this one.
in that context. So when I ask you for reference angles, when you find them for homework, that's what you'll do. Okay? It'll be delta math right out of the book. I'm just waiting to see how far I get the next thing.
So reference angle is like the angle between the x-axis and the whatever.
Always. Okay? So if I pen doesn't always work. Okay, so hang on, let me do a few examples. Okay, coterminal is another word I need to say. We've already had the word terminal side. These are coterminal. 30 degrees is coterminal with -3. Sorry, it's not working. Okay, with -330. Those are coterminal. You better believe we got to be able to go both ways. The positive way is just been defined for a long time to be going up into the first quadrant first, and the negative you feel like you're going down into the fourth quadrant. It feels right. But girls, there's nothing special about spinning one way or the other. Things spin clockwise and counterclockwise, but we have to that's our way of saying which way it's spinning. Coterminal means exactly what it sounds like, they land in the same place. They have the same reference angle. Once I landed there, they're both 30 degrees away from the closest x-axis. Don't do it right now, but in your calculator you could type in cosine of 30 and cosine of -330, and guess what would happen? You get the same answer. Coterminal is really good. Okay? One way to do coterminal, if it sort of gets away from you sometime, oh, by the way, this is also coterminal. 390 degrees is also coterminal. Just agree with that? 390. I went 360, and then what did I do? 30 more? Did you see how you can draw that little spiral to show if you're going around more than once? Okay? So how would I find out how many degrees this is coterminal to the other one? So the first rotation is a 360. The second rotation is a 360, which is 720, so this one's 750. Okay? The sine of 750 and the sine of 30 are the exact same thing, which I'll be teaching you. Okay? Let's see what else I want to say here. Oh, so if you want an easy way, which I'm sure that you do, I don't think a lot of you probably don't need to write this down, but to find a positive coterminal angle, which you'll see in your homework, a positive coterminal angle you can take the angle that I give you and add 360s. I'll put a little S here. If you just start, and girls, the reason I say you don't have to write that down is if you start here and you start adding 360s once you end up where you started from, aren't you just adding rotations to your number? Okay. To find negative angles that are coterminal, what will you do? If you want a fast way to do it without too much thinking, you could take your angle and start subtracting 360s. What was 30 degrees minus 360? Wasn't it negative 330? Let's draw those. Here's 30 degrees. Here's negative 330. Sorry, it'd help if I did it negative. All right, negative 330 would go around and land like that. Watch this. Here's my terminal. I spin around. Sorry, you should have corrected me. This is my initial side. I spin around this way, and this is my terminal side. Same angle. Do y'all see that? So, you know, I can remember a kid named Wesley years ago that I'm like, they're like, how many times? I'm like, as many times as you want. So on the test, it added some insane amount of 360. And I had to go and check and make sure it was coterminal. But anyway, you'll be asked to find those. So, next thing. Okay, so now I'm going to show you with about 10, not quite 10 minutes left, what's going on with our trigonometry. I want you just to watch. I don't want you to write anything down. There'll come a time and a place to write this down. I'll be really sensitive when I give you your homework that is on stuff that I've really laid the foundation to of trigonometry. You may have some of this depending on how far I get, but I'll let you know, okay? So, I'm not even going to draw that right now. All right, so our premise to get started in right triangle trigonometry is that we have a triangle. I don't want to draw it that way. So we have a triangle with reference angle. I'm going to draw a triangle with a reference angle of 30 degrees. That forces that to be 60 and this to be 90, okay? I'm going to make a chart that you will eventually know. I'll teach you a super easy way to find it. But I'm going to put sine, cosine, and tangent. By the way, there's 3 more trig words, secant, cosecant, and cotangent, that I'll teach you. But have you heard those words? Secant, cosecant.
Yeah.
All that means it's a way for me to tell you to flip it over. They're reciprocals. Okay? So once you know this set, you really don't need another chart. You can just look at sine and cosecant, the reciprocal. I'll teach you that later. All right, I'm going to teach you how to do this in degrees and in radians. But radians apparently are not going to happen today if I look at the time, okay? So I'm just going to fill out this chart. I know it is so tempting for you to write, but please don't, because if you're looking up and down, you'll miss the point of what I'm trying to make here. So let's write down everything we know about 30 degrees. And let's go back to what she was talking about, SOHCAHTOA. All right, let's say if this side is, if the hypotenuse is 4, then based on your homework or your memory from geometry, what is the side opposite 30 degrees? 2. And this is, the long side is 2 root 3. And sine is opposite over hypotenuse. And so it's 2 over 4. Would it have mattered what numbers I used?
No.
This ratio is always going to be 1/2. So you just learned something. What's the sine of 30 degrees? I don't care if you've gone to outer space or on your little notebook paper. It's 30 degrees because it's a ratio of your opposite to your hypotenuse. Are y'all okay with that? Because this is A, 2A, and root 3A, right? Okay. Cosine is adjacent over hypotenuse. And this is not special to 4. This would happen with whatever number I used. But what would any of them reduce to ratio-wise? Root 3 over 2, okay? Tangent of any kind of 30-degree angle is going to be opposite over what? Adjacent. Opposite over adjacent, sorry. There are some teachers that call this 1 over root 3. In my class, I don't really care if you write that, but most of us will rationalize it and call it root 3 over 3, okay? Now let's do...
Wait, when you rationalize it, like what you did, you just multiply it by like itself over itself, right?
Thank you. Yeah. Did you answer your own question, Nicole, or do I need to?
Yeah.
All right, now let's do 60. So this is 60, this is 30, and this is 90. I could have actually used the triangle that was up here, but I'll just draw a new one. All right, so somebody make up a size of the hypotenuse. Just volunteer a number.
5, 10, 5.
I don't care. I'll use 10. Okay. All right, so if the hypotenuse is 10, what's the shortest side? 5 and 5 root 3. By the way, you're going to hear the word unit circle a lot. I will show you the unit circle. I don't use it a lot, though, because unit circle means the radius is 1. I'll show you the power of it, but I'm not a big fan because does it even matter what the radius is? So far, I've picked 2 different radii, and you could pick 20 different radii. And all of the ratios would collapse down to what we're writing in our chart. Okay, now, the sine of 50 degrees, in our scenario here, is 5 root 3 over 10. That reduces to root 3 over 2. So of 60 degrees, this is root 3 over 2. Cosine is adjacent to hypotenuse, 5 to 10, 1/2. And tangent is opposite over adjacent, 5 root 3 over 5. Root 3. Do y'all remember a little while ago I said the tangent of 300 degrees was root 3? It probably went in one ear and out the other because you don't know trig yet. But look at what I did. I went to 300 degrees in my head. My reference angle is 60. You'll memorize this. You'll know it would be root 3, but it would be negative. I'll go over that later. Which one's missing in this chart? 45? Okay. All right, 45 degree angle. 45, 45, 90. This is A root 2. We're not going to make up anything right now. We'll just use A. All right, so sine is opposite over hypotenuse. Nicole, this is going to happen again. You're going to get 1 over root 2. I definitely had a few college teachers that use 1 over root 2, but we're going to use square root of 2 over square root of 2. Over 2, sorry. Isn't the cosine going to be the same thing? And it should be, because sine is about the opposite, cosine is about the adjacent, and a 45 is isosceles. They should be the same. That row is actually really easy to learn. Shouldn't the tangent of 45 be 1?
Yes.
If you put opposite over adjacent. Okay, now, believe it or not, in 2 minutes, I have 2 minutes that I will use, I'm going to teach you the chart. You may or may not have to use it for homework. But you'll have it in the notes. I've still told you not to write it down. But probably you can write it down yourself after the next minute. I only have a minute to teach you the chart. Okay, so one of my students told me years ago, his name was Robert Harris, how he memorized the chart. We'll fill in the radians later. So this is the Robert Harris method. All right, so this is radians. We'll fill in degrees. Sine, cosine, tangent. Got carried away. Sine, cosine, tangent. I think most of us say that order. Then he goes 3, 4, 5, 6. Okay? Then he went 1, 2, 3, 3, 2, 1, 3, 1, 3. 1, 2, 3, 3, 2, 1. Look at my fingers. The third row column has 3 3s in it. Okay? 3, 1, 3. How many 3s do you see?
2.
The third one's right here. The first 2 columns are divided by 2. And then square root everything that's not a 1. Because what's the square root of 1? So when you grab a test or a quiz, a lot of y'all like to throw that and then just keep looking at that. Those are all your the reference angles you need to know for now. Okay? I didn't do anything tonight. So as you're leaving, 1, 2, 3, 3, 2, 1, 3, 1, 3, but there's one more, 3. And then the first two columns are divided by 2. This is great. You'll write it down in the next class, okay? We'll get a page to write it on.
Thank you.
Bye, girls. I'll post homework. Huh?
Thank you.
Did it say it on my